society and wanting to estimate with 95% confidence the proportion of households in its county that own at least one dog. All right. So when we're talking about interpreting a confidence level, all right, that is different from interpreting a confidence interval. Do you guys remember yesterday how we interpreted confidence intervals? Can someone share how they or how you interpret a confidence interval from yesterday? That was panic, yeah, but what part was the interpretation part? No, I'm asking, how do you interpret your answer? The conclusion statement, okay? At the very, very end, the conclusion statement, right? So C part of panic, or C part of panic. I can't talk about it. All right, so what did you say when you interpreted this? We are what? 95% confident that the interval from the low bound to the high bound captures the true proportion or true mean, whatever, of this context, right? Okay, so that's how you do it, because basically what you're saying is that your interval, you have a 95% chance or a 95% confident that it captures that true proportion. Do we know if it does? No idea if it does, but we're 95% confident after constructing a random sample and then making this interval that we're 95% confident in our estimate, right? Level's a little bit different. Okay, level says, what if you did this confidence interval again, and you did it again, and you did it again, and you did it again, and then you did it in repeated sampling. Do you guys remember our Hershey-Kiss activity? Where Henry created an interval, and Will created an interval, and Chandler created an interval, and then we did what? We drew those on the board, all right? And what percent of those confidence intervals captured that? All of them in our case. But is that always the case as n approaches infinity or as n gets large? No. What happens with those intervals? What percent capture that true mean, true proportion? 95, whatever confidence level that we're talking about, right? So when you're interpreting a confidence level, first thing you want to do is that this is not for a specific random sample. It's for repeated samples. Does that make sense? So first part, what you're going to do here is you're going to say in repeated sample. In repeated sampling. Because again, I want you to think of literally about that Hershey-Kiss activity. We all took a different random sample, correct? And then we put them all on the board. 95% or whatever your confidence level is, percent of the resulting intervals so 95% of the resulting intervals constructed in the same manner will capture the true proportion or mean of the context. And in this case, what's our context? We're talking about. So I'm actually going to erase or mean. You guys see why I'm going to erase or mean? Yeah. Because I'm talking about the true proportion. The true proportion of what? Households. And it's counting. That own at least one dog.
These ones that it's like we're gonna have to memorize this too.
Yeah, well, you'll need to be able to recognize these. Generally, it's not, you're not going to see this type of question on the free response portion, and this year you did. I'm not really sure. I think this may have been a 2011 free response, so it was probably about 7-8 years ago. A lot of people, guess what they did when they said find or interpret the 95% confidence level? They did the other thing, which is what? We are 95%. They did that.
Is that incorrect or something?
That's incorrect because that's an interpretation of a confidence interval. You're interpreting what your interval means.
So basically,
you're talking about what the 95% means. Does that make sense?
Yeah.
So again, you guys remember, and I'm just going to kind of draw a little picture up here. So you have this P here, right? And that's where your true proportion is. In repeated sampling, you're going to hope that 95% of those intervals capture that. You guys see here that all of these intervals capture P, but sometimes you get that stray one that doesn't. That's what we're interpreting here. We're saying if we do this over and over and over and over and over and over and over again, we know that 95% of the intervals that we construct will capture the true mean or the true proportion. But we never know if one does or doesn't. But we do know if we do this over the long run, 95% of them will. Yes?
In this sort of problem, is the only thing that really changes the context?
Like in terms of the interpretation piece? Yes. Or it could switch from mean to proportion.
Okay.
Yeah. But the idea here is you're doing repeated samples, and that repeated samples and then the 95% of those intervals is literally what it means to be 95% competent at that level. All right? So different samples are going to result in different intervals. The level is not changing because you choose that level or you're given that level. You just need to know what that level means, and that's what this part of the problem talks about. Does that make sense?
Yeah.
Okay. All right, let's move on to part B. All right, did anyone get a chance to answer part B? No? Did you understand what part B was asking?
Was it just asking like if the percent is in the interval?
Basically, yeah.
Yeah, I said it was. Yeah.
Okay, so let's talk about this. So they made an interval, right? What is this part of the interval? That's P hat. What's this part of the interval? That's the margin of error. And the margin of error is comprised of which two things? Z star, called the critical value, right? Times what? Standard deviation of the statistic. And since we're talking about proportions, what does that look like? Square root of P hat. With me?
Yeah.
Okay, so that's what these pieces are. So I want you guys to kind of be like, what do I write on my paper? I want you to make notes to yourself. Like this is the annotation. It's like you're literally going through your problem and identifying what you know and what you don't, because that's going to help you interpret stuff, correct? So in part B, it says a National Pet Products Association they're claiming that 39% of all American households own at least one dog. What does that sound like? 39% of all American households owned at least one dog. That sounds like P. They're saying that they suppose that P is equal to 0.39. That's the claim. They're claiming this. Does the Humane Society's interval estimate provide evidence that the proportion of dog owners in its county is different from the claimed national proportion?
So it's saying is it's different from the.
Basically, it's asking what Chandler said. Is this in the interval or is it not, right? Because do you understand here that this interval from 0.14 or 0.417 plus or minus 0.119, like if you kind of go and you subtract and you add that. Let's go ahead and do that. Did anyone actually do that for me? So let's go ahead and, so Knife, you said you did that. Like, go ahead and tell me what that is.
Subtraction is 0.298.
0.298 to what?
And 0.536.
0.536. Okay. So this is the 95% confidence interval for this, with the sample proportion being 0.1 or 0.417. So basically it says, does the Humane Society's interval, this thing, provide evidence that the proportion of dog owners in its county is different from the claimed national proportion? The answer is no. Why not? Because 39% is contained within the interval. What does that mean? So it's in the interval. So what?
95% confidence that.
Because
True proportion.
That what true proportion?
True proportion of
39%.
The true proportion. Could be 39%. As it is in the interval. So what if that was outside? So what if they said instead of 0.39, 0.28? Yes, it is different because 0.28 lies outside, right? So we don't have evidence to say that like it's different from 0.39 because 0.39 is inside the interval. You guys with me about how you needed to go approach this? Okay. So generally, you caught that on real fast, like you just said, is that in the interval? Yes. But you have to kind of explain what you mean. Okay. You guys good?
Yeah.
Questions? No? How was part C? Could you do part C? It's not right. How many households were selected in Humane Society's sample? What did you say? So Amy's saying 66. All right. So how do we find sample size? Is that when you do that thing? Yes, that's when you do that thing. So this is when you use the margin of error, right? So your margin of error, you know, is 0.119. Do you guys think that's a pretty high margin of error? What percent of error is that? That's about 12% error. It's pretty high. So you take your margin of error, and remember, what do we set that equal to? Because we just talked about it earlier. That's Z star times standard deviation, right? So what's Z star for 95%? You gotta know it, 1.96 times the square root of. Do we know our p hat in this case? No or yes?
I thought the p hat was going to be the 39%, but
That's what we determined that was p, right? Because it said all attached to that percentage. So if that's not p hat, what is p hat? That 0.417, because that's going to be part of your interval. So that should be 0.417 times. What's the complement of that? What's 1 minus that? 0.583. And divide that by n, correct? Okay, let's quickly go through that. You can multiply those. First thing I'm going to do is I'm going to square everything. I'm going to get rid of that square root. So then I have 0.119 squared equals 1.96 squared times whatever this product is divided by n. Because I'm going to find the product of 0.417 times 0.583. 0.2431, 0.2431. Okay. And then what do I need to do to solve for n? Multiply that, move that down, basically switch those, right? It doesn't change. The process in solving for sample size does not change. Like it always does this. So then n is going to be equal to 1.96 squared times 0.2431 over this 0.119 squared. And remember, I encourage you guys to type it in all like this. Like type that in all at once. Using alpha y equals. You want to type that in there, Henry, see if you get it right. I just want to make sure you know how to use the calculator the day of the AP exam. Because it's fun to watch me do it all. Unless you can type it in there. You always round up. Because remember, more sample size is never a bad thing. So approximately what sample size should we be using here if we type that correctly in the calculator? So 66 households, right? This is good for your response to kind of teach you some skills and remediate some skills. All right? Karen, you're looking puzzled. What's wrong?
are you getting hurt?
Yeah.
What's wrong?
What did you guys get?
7.8.
Yeah.
Always.
I thought
You
I
didn't
saw
square
it.
it at the bottom.
Yeah, you did not square it at the bottom.
We didn't.
Yeah, I did. That's squared.
Did you put 0.1192?
No, I put 0.119 squared. Because it's squared right up
I
here.
was waiting for him to.
Well, then you should know you're too smaller.
Look at this. I wrote it twice in a row.
That's a big two. buddy.
Okay, now it's 66.
Sorry, pal.
Smart sport.
Okay. Anyways. Does that make sense now? Now that you got 66? Okay. 0.119 squared, not 0.1192.
Yeah.
All right, cool.
8.
Human.
All right, so today we're going to talk about confidence intervals for estimating means. Now, this is going to be a little bit different from proportions, and we're going to introduce a whole new distribution today to help us calculate these confidence intervals for means. All right. Like proportions, confidence intervals for means follow the same form, as in you will still have a statistic, you will still have a critical value, and you will still have a standard deviation of the statistic. However, you're going to go from p hats and p's to x bars and mu's. Okay? Does that make sense? All right. Recall for proportions we use p hat plus or minus the margin of error, where mu, the margin of error is going to be z star times the standard error of p hat. Do you guys remember the word standard error? I think we talked about that. Standard error is the same thing as standard deviation. They're synonymous. Okay, so some textbooks will talk about the standard error, some talk about the standard deviation. You'll hear me say standard deviation more than standard error. Right? Recall that we use z because the central limit theorem told us that the sample distribution model for proportions is approximately normal if the sample size is large. Okay, you guys remember to check the is large thing for proportions here. You did np hat is greater than or equal to 10 and nq hat is greater than or equal to 10. You guys remember doing that?
Yeah.
This is how you check for the sample size being large for proportions. If you have at least 10 successes, at least 10 failures, your sample size is large. Okay? If not, sample more. To estimate our standard deviation of the statistic here, we use p hat q hat over n. All right, and remember, why do we use p hat and q hat versus p and q? Because p is unknown. We're using a confidence interval to do what? What is the whole point of a confidence interval again? To estimate what? The true proportion, or the true mean, the true population parameter. Okay? Given a sample statistic, kind of like p hat q hat. Right? Today we're going to do the same thing. We're going to estimate sigma over square root n. But today we're not going to be given the population standard deviation. We're going to have to use something to estimate it, and that's called the sample standard deviation, S of x. However, one issue. If our sample size is not large enough, the normal curve will give an incorrect estimation. Okay? So for this, you can have lower sample sizes, but the normal curve does not approximately fit it. So guess what we're actually going to do? We're going to talk about a new distribution that's not normal, but is kind of like a normal curve. And that distribution is going to help us account for this extra error. Okay? So what we're going to do is we're going to talk about the t distribution. All right, so we're going to watch a short video clip now. Let me record myself. So the purple one here is going to be the normal curve. Both the blue one and the dotted red one are the t distributions. All right, so take a look at this. What do you guys notice about the tail area here and the tail area here? This one here, if you were talking about the red one down, has more area under it than the purple one. You guys see that? So it's going to allow for more variability because they were talking about within the video that the barley plants have a lot of variability from season to season. So with a lot of variability, you need to account for that. What they were basically doing is that Gossett was basically the tester for all the beer, so he got to drink a lot. And he decided whether or not to keep that or to get rid of a batch of beer. So if it tasted a certain way. So he used like little sample sizes. Could you imagine if he used large sample sizes? How do you taste test a large amount of beer? You drink it, right? And only one person's taste testing it. So he would have to drink a lot of beer himself. Yeah. So after a while, he probably didn't care how it tasted. So that's why I had to use low sample sizes. But he figured out that like the variability within the Barlow families was actually like the issue, right? Okay. So okay. All right, so it's called the t-distribution. One of the big things that you need to note here, and do you guys see how it's in bold here? I'm going to go ahead and underline it and box it in red. Okay. We use this distribution when we have to estimate the population standard deviation. So anytime we have to estimate the population standard deviation, we're going to use the t-distribution. Now, I need you to understand that the t-distribution and the normal curve behave pretty similarly if sample sizes are large. However, if the sample sizes are small, you're going to use t. And the reason you're going to use t is it accounts for more of the variability with that low sample size. All right? So if sigma is unknown, you're going to use s of x to estimate. And that's going to be one of the conditions that you're going to check as you do a confidence interval. It has something called degrees of freedom. Do you guys see the df on the board? I don't know if you guys saw it on your paper, degrees of freedom.
Mm-hmm.
Basically, that's going to be a measure, and it is basically defined as the sample size take away 1. So if you want to have a specific degrees of freedom, you take sample size, subtract 1. It's basically a measure that we talk about to refer to the variability within a distribution. All right, you're going to use degrees of freedom always for t-distributions and something called the chi-square distribution that's coming down the line. All right, so there'll be a bunch of different degrees of freedom. And you'll actually also use it when you're talking about regression lines. They have degrees of freedom as well. But for right now, you need to understand the degrees of freedom are just basically the sample size minus 1. So if you have degrees of freedom 2 up here, what was the sample size for the red curve? 3. If you have degrees of freedom 9, what was the sample size for the blue curve? 10. You guys see that? Just add 1. Okay. Properties of the t-distribution. Remember, we don't use this when we use this when we don't know sigma. We use this when we do not know sigma. So unless it says population standard deviation equals this, you do not use the normal curve. Okay, you use this curve. So you have to either be given the population standard deviation, or if you're not, you use the t-distribution. So if you do know sigma, you use normal curve. If you don't know sigma, you use t-distribution. It's single-peaked, bell-shaped, unimodal, symmetric. All qualities of what? You guys basically understand that the t-distribution is basically a normal curve, but not. It's like a faux normal curve. It's like a synthetic normal curve. And its job is to account for the extra variability within small sample sizes. Right? Sarah, you have a question?
Do we need to go over and like how it's different? Like
It's different because of the tail areas. Okay? So do you see this dotted red part right here? The area under this is basically when we account for like what we call T star in this case. But do you guys remember when we were talking about Z star and negative Z star? That was the tail area. Okay, and we usually like shaded in the whole curve and said we were doing like 90% confidence, correct? Do you see here that the tail area for that red one is a lot higher than if you were to use the normal distribution, which is the purple one here?
Yeah.
That's what its job does.
okay.
It accounts for the extra tail area you get. And the reason you have extra tail area is due to the low sample sizes. All right? Low sample sizes have more error. You guys agree with that?
Mm-hmm.
So how do you reduce variability? But what if you're not able to have more sample size? Then that's why we have this secondary distribution. Great, any question? Does it still have an area 1? Yes, sir. It does. It has a lot of the same properties. The major difference between the two is the amount of tail area. Okay. However, as that increases, as the degrees of freedom increases, which means as sample size goes up, this t-distribution will look more and more and more like a normal curve. So basically, if n is approaching infinity, you have less variability, and that means that your t stars, which are going to be your upper t scores, you guys see why we're changing from z to t? New distribution. Your T stars will get closer and closer and closer to your Z stars. Because for 95% confidence, what is Z star for 95% confidence? 1.96. This will get closer and closer to 1.96 for 95% confidence as sample size goes up. However, this T-score here will be higher. It'll be like 2.132 or something. And the reason it's going to be higher is because of this extra area underneath. It's accounting for that extra variability. All right, what do you need to take away from the T distribution so far? When do we use it? When we have small sample sizes. And when we don't know sigma. That's the key thing. When we don't know the population standard deviation, because that's no longer constant, when it's changing, when that variability of the sample is changing. You guys get here that, like, if you knew sigma was 5, that's constant. It's not changing. It's 5. It's always 5, right? But if you're using S of x, in one sample, it could be 4.3. In the next sample, it could be 4.8. In the next sample, it could be what? 5.2. In the next sample, it could be 5.4. But over time, S of x bar is going to approach a specific number, right? And hopefully that's going to be 5. But do you see that this is changing? That's the variability that you're accounting for using the T distribution. Hope that makes sense. Okay, those are the two major things. All right, go ahead and copy down for your one sample T interval. Notice that we don't call it a one proportion Z interval. It is a one sample T interval. One sample refers to means. T interval means that you're using the T distribution. And the reason that we use the T distribution is that oftentimes sigma is unknown. We don't know. Use a lowercase t. You do not use a capital T. You use a lowercase t. All right. Do you guys understand that this still here is the point estimate? Our point estimate is changed. That single value of this that hopefully represents the population parameter is now changing from p hat to x bar. You guys see that instead of a p hat, there's an x bar. Instead of a t star or a z star, excuse me, instead of a z star, there is a, because you're switching distributions. Why are we switching distributions? Generally, sigma is unknown, and we have smaller sample sizes with means. So we're changing distributions. So t star, critical value. This thing, look at the board for 7.3. What was sigma x sub x bar? What do we define as sigma sub x bar? Sigma over the square root of, this time we do not know this, correct? So guess what we use to estimate? And that's exactly what you come up here and notice that that's written there. So that's going to be your standard deviation of your statistic, okay? Guess what all this together becomes? The t star plus or times the standard deviation over the square root of n. What do we refer to this joined together as? Very good. That is the margin of error. Okay. You guys see that the components are pretty much the same, except that you're switching from proportions to means, and now this time we're having a t distribution, correct? Okay, so it's a little different. Okay, now we're going to use S of x when sigma is unknown. So we're going to use S of x when sigma is unknown. All right, so here are the assumptions for a t distribution. First thing, just like what you had for proportions, you need to check for randomization. Was there some sort of random sample, simple random sample, random assignment? Was randomness used to collect your data? So you're checking for that. So that's a similarity between the two. You guys with me? Between the similarity between the two? Here is the new one. I'm going to star it here. Sigma is unknown. So if sigma is unknown, we're going to use S of x to estimate. And when we use S of x to estimate, that implies that we're going to use what we call T procedures. That means that you're going to use a t-interval, a t-test, a two-sample t-test, a two-sample t-interval. All right, but today we're doing one sample for t. So that means you're going to use those t procedures there. All right. The last thing here is going to be normality or approximately normal. So again, this is the same thing that we did in 7.3. If your population's given that is normal, so will the sampling distribution. Same idea. Large sample size. Generally, what constitutes a quote-unquote large enough sample size? We say that's greater than or equal to 30, correct? And what theorem allows us to talk about that? Central limit theorem. Now, on your quiz, I said if you name drop, you got to explain why the central limit theorem can be applied. Some of you guys are like, we can just use the central limit theorem. Well, why? Because the sample size is large enough, since it's greater than or equal to 30. Now, that's just a rule of thumb. You're looking for a large enough sample size. This is just like a rule of thumb, that 30. Okay? When we talk again, we're going to bring this back tomorrow. We're not going to finish all of means today. We're going to talk about when you have lower than 30 and you're not able to assume normality using the central limit theorem, or it's not given to you that it's normal. You're going to have to graph the data, and you're going to have to check the shape of your sample data to see if you can use the normal distribution to do that, or the approximately normal distribution. Or in this case, it's synthetic normal distribution, aka the t-distribution, right? Okay. These are the three conditions you're going to check. All right, how to find t star? You could use table B if you want to, but we're not going to do that because we're going to use technology in this course to kind of do that. All right. So what we're going to do here is we're going to mark out, use table B. We're going to use our calculator. I'm going to show you how to do that. You do not need to write this down. We're not using table B. But we are going to need to know that the degrees of freedom is n minus 1. You will need to know the degrees of freedom are n minus 1. All right, so we're going to do this first example here with 90% confidence when n is equal to 5. Okay, so 90% confidence when n is equal to 5. Now again, you're going to do the same thing that you did for normal distributions, but this time it changes. Okay, do you guys remember that when we did this for z stars, you shaded in this area, and we called that what? 90%, right? So how much area is technically left over? 10% with 5 on each side. Yes, sir.
Sorry, I had to laugh. There was Karen.
Okay.
I was just coming by to say,
Hi. Well, this is awkward.
for the record, it's been stated, I don't come by to say, hey, enough. You are now my witnesses that I have.
Well, it doesn't have to be during second
Combined.
period. It could be at any point.
Right. But we now have proof, right? Thank you all.
Okay. Sure. Okay. What if I can edit that out from YouTube? I just hope they're just enjoying that. So, all right, TI 84. All right. So, take out your calculators. I'm going to show you how to do this. Calculator there. Okay. No, I have a trial left. Cool. All right, so you guys have your calculator out?
Yeah.
Okay, so clear that out. Now, again from yesterday, or earlier, I guess I should say, is that we were talking about this area below this upper z-score, but now we're going to call it a t-score. You guys remember that?
Mm-hmm.
So what area is below this t-star? So we have 95% of our area below that, right?
Mm-hmm.
You guys see that?
Yeah.
So we're going to use this in just a second. And what's your sample size again? 5. Okay. Now, if you were talking about the degrees of freedom for this little curve that we just drew,
4.
that would be 5 minus 1, which will be what? 4. All right, you with me there? On your calculator, in the same menu, that you go to for normal curves, so second vars, do you guys see that there is a inverse t for number 4? Do you guys see inverse t? That helps you find t-scores. Kind of like how inverse norm helps you find z-scores. You with me?
Yeah.
It's the same thing, just switching distributions. What are the two things that it asks you for when you're talking about a t-score using inverse t? Ask you for the area and ask you for degrees of freedom. You need two things. So what area were we using there? 0.95, right? And what was the degrees of freedom? 4. So for a 95% or 90% confidence for n equals 4, what's our t-score or t-star? 2.132? All right. Don't look at that one. All right, so here, I want you guys to notice that's what we got, right? Mm-hmm. Now, I want you to compare that to 90% Z star. What's the 90% Z star? You guys have this one memorized. 1.6. Which one's higher? The reason it's higher? Because of the more variation. This T star will get closer and closer and closer to 1.645 as sample size increases. So let's go back to our little thing. So let's go hit second vars. What if I go down to inverse T and I did 0.95 and let's say I did 99 because I have a sample size of 100. You guys with me there? How close is that to 1.645? Close. And as n approaches infinity, guess what it's going to do? Get closer and closer and closer to the normal curve. All right. The reason these t-scores are higher is because it's accounting for the extra variability. Yes? Thumbs up? We understand? Cool. No thumbs up. Nice. All right. Cool. How about you do the next one? 95% confidence for n equals 15. Right. So you try the next one. See if you get that one. Right, so I gave you the area and the degrees of freedom you should have used. Did you use 0.975 and 14?
Yep.
Okay, everyone understand where 0.975 and 14 come from? Super important, because I literally told you you're going to get really good at this, and you want to know why I have to get really good at this? You have to, there's a specific Z star for every different confidence interval. There's not memorizable ones for T star. Because why? Why is there not memorizable ones? Why can't you memorize it? A different DF every time because the sample size is going to vary every time. Okay? So you have to know how to do this idea. I told you to get really good at it. It's just kind of first time when you see it, it's kind of weird. So what you guys get as your T star? 2.145? Excellent. That is the correct answer. All right. You guys good with finding that? The area? Again, do you remember how we did the from negative T star to positive T star? This is the 95% from this.
Yeah.
So what percent is left over? 5%. That's evenly split between the two tails.
Yeah.
T star is the upper T score. So it's the higher one, right?
Okay.
So any area below that is what you're going to put in inverse T. So that's 95%. So that's the 95% there, plus the 2.5% over in next, which is why it's 0.975. Okay. All right, let's do example 4. It says a medical researcher measured the pulse rate of a random sample of 20 adults and found a mean pulse rate of 72.96 beats per minute with a standard deviation of 3.6 beats per minute. Assume pulse rate is normally distributed. You guys should be on the lookout for statements like that. What does that mean? Pulse rate is normally distributed. That means your population distribution is what? Is normal. Does that make you guys happy inside? That makes me happy inside. This does not mean you use the normal curve for Z star, because do you guys see this standard deviation here? This is not the population standard deviation. This standard deviation came from where? It came from the random sample up here. You guys see that? So this right here, that is S of X. You guys with me that that's S of X? And what is this 72.96 beats per minute? That is the sample bar, or sample mean X bar. We're going to compute a 95% confidence interval for the true mean pulse rate of adults. All right. So what does that mean we're going to do if we're going to construct and interpret a 95% confidence interval for the true mean pulse rate of adults? You're going to panic. Yes. You guys remember us learning that yesterday?
Yeah.
Hello?
Hello.
Okay, cool. What's the first part of panic? Parameter. We want to estimate, not P. What are we estimating today? No, we're not estimating X bar. We know X bar. You do not estimate sample statistics. You estimate population parameters. That's going to be mu. Okay, you're going to estimate mu, which is the true mean pulse rate of adults. You do not estimate something you already know. It's like this. Let me estimate Karen's age. Oh, wait, cool. I can just go look it up on the Power School and bam, I know, right? We don't estimate things we know. You estimate things you don't know. We don't know mu. Probably should say with 95% confidence. Get off my water bottle cap. All right, so we state our parameter, correct? What's next? How many are there?
20.
Oh,
20?
no, I'm thinking.
That's a lot of assumptions we're making.
3.
There are 3. First one, most important one. Do we have a random sample? Stated it was a random sample of 20 adults. You guys see that's kind of a low sample size, 20 adults? It's not that many. When you're usually talking about means, you're going to have low sample sizes. And that's okay to have low sample sizes, because we have a distribution that accounts for the variability from low sample sizes. Thanks, Guinness dude. All right, what are you doing now?
The
Normality check, right? We were given that pulse rates were what? Good, they were normally distributed. So what does that mean about the sampling distribution of pulse rates? They're also normally distributed. Do you guys remember this is the bullet point when the population is normal, the sampling distribution is normal? This is literally the stuff from chapter 7. We use it in chapter 8. This is why they pair well together. All right, and what do we not know? Sigma. So sigma is unknown. So what do we use to estimate? S of X to estimate. And you know what this kind of invokes here? Like this statement? This is going to be us using the T procedures. This is what's going to invoke us using the student's T distribution. Now for homework, do you think all of these distributions are going to be normally distributed? No. So what if they're not? What's the next thing you check? So if it's not giving to you that the population is normal, what do you check? Sample size is big enough. And what's big enough, quote unquote?
30.
We're looking for 30 or more because of the central limit theorem, right? Okay. And what does that tell you? So sample size is 30.
Then
I'm using the central limit theorem.
mean sample distribution.
The sampling distribution of X bar will be
Oh,
approximately normal. No, normal. Gotta use
Could be
approximately.
that.
You will not know.
Was it a check?
It could be, but it's probably not. All right. Name the interval. Today's interval test, which I will now write on our inference procedure board. Number 2, the one sample t interval. Once a day, guess what I'm going to do? Write it on the board. Tomorrow, we don't have to write another one. Tomorrow, we're practicing with this, but with low sample sizes. So wait, what if you do if it's below 30 and it's not normal?
Yeah, you can go.
No solution. Give up. I quit. No, you actually have to graph it, David. You got to graph it. All right, next interval. So here's your interval for today, folks. X bar plus or minus t star times s of x divided by the square root of n. What I think is very helpful once you write this is basically going through your problem and organizing all the information. As in, like, what's x bar? What's t star? What's s of x? What's n? This is something that I personally do. So I encourage you doing it. I mean, you guys do you, but I mean, I do this. From earlier, 72.69 for the mean, right? What's s of x? What was that? I don't have the paper in front of me. 3.86. I do remember the sample size was 20. All right, what's the only thing that we don't know? But we can find it, correct? But we're not writing this on our calculator. Or not writing this on our paper. Because we're not showing them. Because you guys are still on restriction. Oh, did I close off my calculator? Oh, I did. No, I didn't. Oh, I didn't. I did. I'm done. All right. Smart. TI. Smart. There it is. I don't know why I clicked out of that. That seems dumb. No, I still want to continue with the trial. Okay. So we're going to go second vars. We're going to go down to inverse t. Now we got to do this quickly because this is going to take a lot of time if you can't do this quickly, right? So we got to ask yourselves, all right, what confidence level are we at? 95. So what area should I be using? 0.975. Do you guys see how you have to kind of know that instantly? If you don't know that instantly, you need to come in for some help. All right, you got to know that. Degrees of freedom. 19. How did you get that?
1 minus
N minus 1. All right, and then what do I get here? 2.093. You guys with me there? 2.093. So I'm going to come over here and I'm going to do 2.093. And I think we should write degrees of freedom. Sometimes on the AP exam they count it in the rubric, sometimes they don't. But we could just show that real fast by doing 20 minus 1 is 19, correct? Just making sure we have that somewhere on the paper. All right, so let's put this together. So that means I have 72.69 plus or minus my t-star of 2.093 times 3.86 over the square root of 20. So I put it all in the formula there. First thing I'm going to do is I'm going to take care of that 3.86 divided by square root 20. So 3.86 divided by square root 20. And what does that give me? 0.8631. You're not going to compute with us, Henry? You're too good to compute this with us? Apparently Henry's too good to compute with us. 0.8. I forgot what it was because I was fussing at Henry. 0.8631. All right, and then I can go ahead and multiply that by what? 2.093. So times it by 2.093. So 1.86807. 1.807. 1.807 around. 2.86. All right, so let's do this. I have the minus version. I have the plus version. So 72.96 plus second answer. Is that 72 point? Actually, let's just do this. Oh no. Oh boy. Oh no. Second mem. Oh no, not second mem. Second enter. Second enter. Oh yeah, it's gone. It's gone. You were computing now, Henry? You already done? Okay, cool. Well, help me out here because I'm bad. No? Okay. Cool. No, I don't want your help now. No, I got this. 72.96 or 69 plus 1.087, right? And 72.69 minus.
Big battery.
Oh, I did it again, didn't I?
Oh, yeah.
I am off the game today. And I'm going to do 72.69 plus 1. Oh, I did 72.69 plus 1. All right, how about this one? Did you guys get 70.883 to 74.497? All right, help me remember that. 70.883 to 74.497. All right, so that's our interval, right? Okay, let's see if my PowerPoint is the same. All right, so I'm a little off, but this is okay. Well, no, this answer is a little off from what's on the PowerPoint, but both are okay. So if you're in the proximate kind of guidelines, you're all right. Now, what I will show you is that you can use your calculator. So now let me show you how to do that on the calculator real fast. All right, you guys remember going to stat and going over the test yesterday? Okay, so let's go find today's one. Not t-test, t-interval. You guys see number 8?
Yes.
So you could either put in data or you can put in statistics. Data means that you type stuff in L1, like the lists. Did we type anything in the lists? No. So go over the stats, and you guys see how that's like gives you X bar and places to put everything? What do you say X bar was? 72.96? Or 69?
Keep saying that.
I'm just transposing. I'm trying to keep you guys on your toes. Make sure you're here. Yeah. Okay, or just trying to confuse you. Or I'm bad. That's true too. That's exactly. All right, so 3, was it 3 point what? 86, and then N was 20. What's our confidence level? 0.95.
What?
Is it 0.95? It was 95%, right? So confidence level is just the 95%. You don't put the, because you're trying to put in the area. So the area, so yeah. Were we close to that? Yeah, we're pretty close to that, right?
What?
I actually got it on the money.
Right, that's exactly right. Yeah, I got.
You got this?
Yeah, I got it exactly.
All right, so check to see what you're typing in there on it. All right, so let's go ahead and conclude this, because now I showed you how to do it in calculator. We are 95% confident that our interval from 70.83 to 74.55, or you guys can do your 3 decimal places, it doesn't matter. As long as you have your interval from up here coming down there, that's fine. The only thing that's going to be different for means is that you need to say units. You have to include units here. So you got to do units there. So our units were beats per minute because we're talking about the average heart rate. So beats per minute there. captures the true mean of the pulse rates of adults. So what are some of the similarities and differences between one proportion z intervals and now a one sample t interval? Nothing. They don't have any similarities, no differences.
There's basically.
There's more assumptions.
You have to do more assumptions.
There's more assumptions, like one more. Okay.
You have to put units in the conclusion.
Units in the conclusion statement. T versus Z, right? Whole new distribution. Still have to do panic. Panic's pretty much the same, right?
We should do pain C.
Pain C? That'd be weird. Okay, so what if you had a follow-up question? Another medical researcher claims that the true mean pulse rate for adults is 73 beats per minute. Does the confidence interval provide evidence to support or refute the claim? So think about your interval. Like, what does the 73 does? Is it on the inside or outside? So does it support or refute? Since it contains the 73 beats per minute, there is no evidence to doubt the claim, aka, I guess, it supports the claim. We're going to be getting questions about whether certain things fall inside or outside the interval, because that can be a way that you do hypothesis testing. You can actually construct an interval, and if a certain number is inside or outside, you can either what we call fail to reject the null hypothesis or reject the null hypothesis. It's coming down the line, but you need the skill about being able to assess a claim or a question about and use an interval to see if a value is either inside or outside. So does that make sense why this one kind of supports the claim, aka there's no evidence to doubt the claim? Good. All right, we have that one last example at the top of the page for determining sample size, and we are done for the day. So this is going to work very similar to yesterday. I think sample size for this is much easier. Much, much easier. Okay? So let's talk about that. So here, if we want to determine a certain margin of error, we want to be able to find a certain sample size to attain that margin of error. However, a couple things have to change. Notice your margin of error here and how it's similar and different from the one that we wrote earlier when we did our confidence. What do we have instead of T star? We have Z star, which means, do you guys notice that sigma is known here? Okay. Why do you think we have Z star and sigma known this time versus T star and S of X? Well, T star is based off two things, right? Knowing the area and the degrees of freedom. And what are the degrees of freedom? How do you calculate that? If you don't know what n is, question mark, question mark. If n is what we're trying to find, can you find the degrees of freedom? No, that would be question mark as well, correct? Which would mean this would be question mark, which means, could you do it without knowing sigma? No, in these cases where you're finding the sample size for a mean, or the margin of error including a mean and a standard deviation, you actually have to know sigma here. All right. So this time, sigma will be given, and when sigma is given, you use Z stars. All right. So if sigma is given, you use Z stars just like normal. When do you use T stars? When sigma is unknown. You guys see that? So if sigma is known, use the Z stars that you've been talking about. If it's unknown, that's when you use this new T distribution. You guys with me here? Yes? Okay. Because we couldn't actually do this unless we knew the sample size, like to find T star and all that stuff. Can't do that. Again, you always round up to the nearest person. Always round up to the nearest person. So always round up to the nearest person, regardless of what your decimal is. Always round up. All right, so let's do this last one and we're done for the day. The heights of EHS male students is normally distributed with sigma equals 2.5 inches. Do you guys see that they give you the population standard deviation? At that point right here, if they give you this, that means that Z star is going to be known and you use that. How large a sample size is necessary to be accurate within 0.75 plus or minus inches with a 95% confidence interval? All right, so what we're going to do is we're going to use our margin of error, which is now not going to be T star, it's going to be Z star times the sigma over square root of it. All right, what do you know? I definitely know sigma is what?
2.5.
So I'm going to say this is 2.5. Do I know the margin of error? 0.75, right? That's counted for, that's counted for. What's the only other thing I haven't used? Well, that's what we're trying to find, correct? This is how large a sample is what I'm trying to find. And here is what I don't know. 95% Z star, right? And that's going to be? 1.96. Do you guys agree that I can rewrite this as 1.96 times 2.5 over the square root of n? And that's equal to 0.75? Because that's not, like, this is how you know it, because it's the critical value times the standard deviation. I'm just joining them together so it makes solving for n a little bit simpler. Now, you can go ahead and multiply these. We can actually multiply it. So if you know that, like, you can rewrite those, like, those being the 1.96 and the 2.5 on the same numerator, you can go ahead and multiply those. What's 1.96 times 2.5? 4.9. Confirm, somebody?
Yeah.
Henry, that was like the fakest attempt of putting something in the calculator I've ever seen in my life. You picked it up, you literally typed one button, and then you put it face down. And you're like, yeah, I can prove it. Okay, cool. All right, so what do I do here? So 4.9 stays the same. Remember, what are we doing to solve for n? Multiply it over, divide down. You guys remember us switching those earlier? So this would be the same thing as the square root of n equaling 4.9 over 0.75. So then what would I need to do to get rid of the square root? Square everything, right? So then my n will be what? 4.9 squared over 0.75 squared? Nice job, Henry. What's the answer? What did you get?
40. What are your outcomes? Right. So
I don't know. Do we round?
Yeah.
Yeah.
I think we round down, right?
40.
Oh.
42.7 human beings. There you go. Man.
So 43 studs, right? All right. How do you guys feel today about one sample t intervals?
Okay.
Okay.
All right.
Okay.
So what do you
I know.